Hey guys, welcome back. My name is Dear Tiagi, and today we'll be going over area of polar curves for the review for the AP Calculus BC 2025 exam. So to start, let's try to derive the formula for an area of a polar curve. When we have a circle, let's say a circle like this, we want to find the area of a sector like this with an angle of theta. How would we find it? Well, we know that the total area of the circle is pi r squared, right? Pi r squared. I don't know why I'm writing the r like that. Pi r squared. And we want to find only the area of this sector here. So we know that the total angles in a circle is 2 pi. So the total angle from here all the way there will be 2 pi. So we multiply by theta over 2 pi to get just this portion here. And once we do that, we get the formula for it. The area of a sector is r squared times theta over 2, or 1/2 r squared theta. Now, let's try to think about how this would work for a polar curve. Imagine instead of taking a theta, we have another curve. Instead, we take a really tiny amount, d theta, okay? And so we have a d theta and r squared. And let's say we have some curve, like so, and we keep taking these tiny d thetas and r squares, and we keep doing it over multiple tiny intervals. We integrate that, finding the area of all of those. Now, if we multiply by 1/2, which is again the area of a sector, so we multiply by 1/2 here, we will get the area of a polar curve. So the area is 1/2 the integral of r squared d theta. We also make note that there needs to be bounds on this integral, right? Because we're not taking an indefinite integral, we just want to find the area from here to here. So what we have to set is the bounds from a, alpha, to beta. So from this angle beta to this angle alpha. And that's the formula for an area of a polar curve. And again, we derived it by looking at a circle and then imagining if we had a curve and we used this same formula for tiny amounts, from infinite amounts, tiny amounts from here all the way to here, and we added them all up. That would be the area of that polar curve. So let's try out some problems now. For the first one, let's say we're given the curve r equals 2 sine theta minus 2. And we want to find the total area bounded by that curve. So I'll draw a quick graph of the curve. So this curve is only graphed from 0 to 2 pi. That's the interval, and it looks like this. So in this case, the area of the curve would be, because we have to go from 0 to 2 pi, that's the graph. It's graphs from 0, so starting from 0 at -2 here, all the way to 2 pi, which is back at 0 here. So it goes through one complete cycle in this interval. Therefore, the area, using our formula, is 1/2 the integral from, again, 0 to 2 pi, that's the entire curve, times r squared. R squared is 2 sine theta, or so not times, just inside that, minus 2 squared d theta, and that's the answer. Next, let's do another example. Let's change it up a little bit. Let's say it was r equals 2 sine theta minus only 1, and we wanted to find the area of the inner loop. So as a refresher, the curve of this looks like this. So we start here, because we start at 0, so to 0, we get 0 minus 1, which is -1. So we start right here. Then we go here, because we see that if pi over 6 equals 0, and we do a little loop here, and there. So what we want to do is we want to try to find the area of this inner loop here. To find this area of the inner loop, we know that the formula is going to be a equals 1/2 integral of 2 sine theta minus 1 squared d theta, but we don't know what the bounds for this integral should be. To find the bounds, we need to figure out where the function hits here, goes here to here, and hits back. So at this point, the r equals 0. So we want to find the first 2 points where r equals 0. So we want to find 0 equals 2 sine theta minus 1, which equals sine theta, which equals 1/2. And this is only true when theta equals pi over 6 or 5 pi over 6. There are other cases too, but we only need these two bounds because, again, think about the function. From here, we start at theta equals 0 because we get -1. Then we go here, theta equals pi over 6, and we could go through the loop, then back here at theta equals 5 pi over 6, and then the function keeps going until it comes back here at theta equals 2 pi. So the bounds of the function should be pi over 6 to 5 pi over 6, because again, that's when it starts the inner loop and ends the inner loop. So pi over 6, 5 pi over 6, and that's our final answer. Next, let's do an example with two polar functions. Let's say we want to find the area bounded by theta equals 1 and r equals 5 cosine theta. So for this one, let's do a quick graph. So it would look something like this. And we want to find this region here. So in this case, again, the formula for a polar curve, we set that up. And now we just need to figure out the bounds. So we see that we want to go from here to here for our bounds. So here, theta equals 1, that's given to us by there. And here, this is the line, theta equals pi over 2. And this makes sense if we think about it functionally too, because at theta equals pi over 2, cosine equals 0, and therefore it's touching the line theta equals 1. So our bounds are therefore 1 to pi over 2, and that's our answer. And one more problem before we end this video. This one is a little more challenging, but we'll get through it. So this one, it's asking us to find the area bounded by r equals cosine theta and r equals 1 plus sine theta. So whenever you're given two polar curves like this, I recommend trying to visualize how it looks, or if they don't give you a graph, then just try to graph it. So in this case, we get a graph that looks something like this. So that's 1 plus sine theta, and then cosine theta would look something like, something like this. So now what we want to do is we want to find this area and the entire area, like this to this. So if we look at the curve, what we can do is we can break it up into two components, two integrals. We can first take the integral from here to here of this curve, of the cosine theta curve, and we can take the integral from here to here of the 1 plus sine theta curve. So the idea here is we're breaking it up into two integrals that we can then add together. So in this case, we want to first find cosine theta, the integral from here to here. This is 0, this is pi over 2. So our first integral bounds, our area, is equal to 1/2 the integral from 0 to pi over 2 of cosine squared theta d theta. And then our second one is for the 1 plus sine theta curve from negative pi over 2. And again, at negative pi over 2, it equals -1, and therefore it equals 0, so it's right here. And then to 0, where it goes here, and equals 1. So therefore we want to find negative pi over 2 to 0, the area of the 1 plus sine beta curve. So like so. And that's our final answer. So again, just to reiterate what I said before, the process here is we look at the function, we try to divide it into two areas or multiple areas that we can add to find the total area. And that's how you solve for the area of a polar curve. Thank you guys all for watching, and be sure to subscribe for tomorrow's video. Thank you. Bye.